in what was proven to be an important and informative series. Everyone here recognizes that AI is already having an enormous impact on society. AI researchers are helping make autonomous vehicles safer, our defense systems stronger, and the world in general a better, smarter place. That's why it's so fitting that our modern artificial intelligence series, now in its second year, is happening here at a school whose mission is to create technology that can be used for the benefit of society. NYU Tandon is fast becoming a global center of influence in the field, thanks to entrepreneurial efforts like our AI Nexus Lab, an accelerator program that supports AI-focused startups, and academic centers such as AI Now, which is bringing together experts across computer science, economics, law, academia, and other sectors, and which is incidentally the first AI research institute founded and led by women. Tandon itself, in fact, is now an institution led by women. This fall, we welcomed Jelena Kovacevic, the first female dean in our school's 164-year history. Soon after her arrival, she gave the convocation address to the class of 2022, a class in which 42% of the students are female. That's an impressive statistic when you consider that the national average for engineering schools hovers around 22%, and it stands as a testament to Tandon's long-time commitment to closing the gender gap in the STEM fields. I would like to thank former Dean Katapali Srinivasan, current Dean Jelena Kovacevic, as well as my own Department of Electrical and Computer Engineering, for hosting this series, which is evolving into a significant venue for those of us working to develop new machine learning techniques and technologies. Now let me introduce our esteemed speaker and tell you a little bit about her. Anima Anandkumar's CV includes time as a postdoctoral researcher at MIT, an assistant professor at UC Irvine, a visiting researcher at Microsoft Research New England, and a principal scientist at Amazon Web Services. She currently holds the Brand Endowed Chair in Computing and Mathematical Sciences at Caltech and is the Director of Machine Learning Research at NVIDIA. She has been the recipient of an Alfred P. Sloan Fellowship, Google Research Award, and NSF Career Award, among numerous other honors. She is widely celebrated for spearheading the development and analysis of tensor algorithms for machine learning, and I hope you will join me in welcoming her for her talk, The AI Trinity, Data Algorithms Infrastructure. First, though, before Anima comes up, I would just like to invite you to remain in Brooklyn to hear a second fascinating speaker at 1, here in the same auditorium. Kai-Fu Lee, Chairman and CEO of Innovation Ventures, will join us to discuss how the AI revolution will be different from previous technology revolutions and the challenges and rewards this will pose. But without further ado, let me invite Anima Anandkumar to the stage. I know that we are all in for a compelling and insightful presentation.
Thanks a lot, Anna, and thank you everybody for having me here. I'll try to not block the screen. And also to the online viewers, I think it's a great community service to also have streaming because everything today is global, and it's great to have AI reach out to the world. Right, and really amazing to hear the efforts to push AI even more further in many different ways. So today I'll talk about what does it take for AI to be successful, right, in a practical setting, and how we as academicians or even theorists, how do we kind of help towards that goal? I mean, the deep learning revolution has shown how many things that we didn't think would work in theory are actually working very well, right? So there are indeed a lot of gaps between what we think in academic research, what we think in theory, and how that translates to practice. And my mission has been to try to really bridge that gap and ask, how we can do that. And being both, having one leg in academia and one leg in industry also, I think really helps me, every day question this, like, am I doing the right assumption? Am I making the right assumptions for my theory? I mean, in practice, is this the right technique that would work well? So it's really this feedback loop, I think, is really critical. So usually in academic research, a majority of time we spend is on the algorithms, right? How do I design the best algorithm? What kind of guarantees does this have? How many samples does this algorithm require? What's the computational complexity? Which are all great questions. We should certainly continue to answer them, but it's not only about that, right? So that's why I have this Trinity, which in addition to algorithms, we have two other pillars. One is the data, the other is the compute infrastructure. And both are equally, if not more important than algorithms. You really need all these three to come together to make AI successful in practice. And I'll show you now how we can think of research that tries to unify these three pillars together rather than think of them in isolation. Right, so that's what I think about these three different pillars. So when it comes to data, how is it usually done in practice, right? So in academic research, we have the benchmarks. We have established benchmarks like IMAGENET for image classification tasks and similarly for others. So mostly academic researchers don't think about data unless they're creating a benchmark. And even then, they create the benchmark, and then it's all about the algorithms, right? So whereas in practice, if you want to solve AI in a new domain and you want to continuously improve your accuracy, you really want to do this in a loop. So you want to continuously keep collecting data based on how your machine learning model is currently performing. And that's where I'll kind of think about what data collection strategies can improve our requirement of labeled samples. I mean, with the advent of deep learning, there is indeed a large sample requirement, right? So most deep learning systems require millions of training examples, and that's just not feasible in many domains or too expensive. So can you try to minimize the sample requirement, and can you do that in an active way by having data collection in the loop with machine learning? Right, so that's the first question I'm going to tackle. The second one is, so how is usually data collected in practice? You have human annotators, usually crowd workers on platforms like Mechanical Turk that label images or text. And in this setting, there can be error prone, right? So if they're not the experts, they tend to make errors, so you cannot completely trust what they're labeling. And so in order to minimize that error, people usually have a number of annotators and take the majority of them as the ground truth. And we'll see how this can be wasteful. I mean, typically people even have 10 or 20 annotators per example, and this is a lot of time and effort to label if you're labeling millions of images. So how do we minimize that requirement, and what sophisticated techniques can we have which treats, again, an aggregation process as a stochastic, noisy process and puts that in the loop with training the machine learning model. So it's not in isolation from rest of learning. Right? And the last part, I say augmentation. People usually think of data augmentation as some very simplistic rule, like you crop the image, you add some noise, something, or you drop out, right? So you do very simple things that to augment your data or to augment your training process. But it can be, for me, this is the kind of whole bag of techniques that improve generalization. So typically, by now, we've figured out very well how to get the training loss to zero, really optimize on our training data set. But we are not always able to generalize very well, right? And especially in NLP, I would say it's still a big issue of overfitting. So how do we come up with better techniques that can improve our generalization? And it has started with simple data augmentation techniques where you take the image, you come up with maybe some different crops or different angles, slightly vary it so that there is enough variation in your training data. But can we go beyond that? How do we come up with techniques that either include generative modeling, that include domain knowledge, that can better help us train and generalize well? And so that's where I will deal with data augmentation as a field. So that's the first pillar on how data is so crucial and how we can minimize data requirements and how we can really treat the whole process of getting the data in the loop with training the machine learning model rather than in isolation. So in the second pillar on algorithms, there is indeed a lot of work, right? And including some of the work that I did on tensor methods, you could think of them as designing algorithms that expand to more dimensions. Mostly we do linear algebra or matrix methods in our machine learning techniques, how we can expand that beyond to look at multidimensional algebra or tensor computations, and what does that mean, right? And what does that give us beyond just matrix computations? So there's an extensive line of work. I won't go into the details, but mostly touch upon the software frameworks we've created that are flexible and make it easy to train at scale, and also show how with neural network architectures, when you use the term TensorFlow or a tensor core, what you really mean is you're transforming an input tensor to an output tensor, right? So it can be a multidimensional in input and output. But currently our neural network layers are all linear algebraic. So can we go beyond and expand the set of operations we do in these layers and fully exploit higher dimensional information? Whether it's higher dimensional information directly in the data or the higher order correlations in the data. So I'll kind of describe how we can build these tensor computations to give a new family of neural network architectures. So that's one thread I'll cover in algorithms. The other is actually kind of thinking of algorithms and infrastructure together, right? So the third pillar is how we want to deploy all these systems at scale. So as we have, our data is growing as well our models, right? So we have now settings where there can be petabytes of data, and then we have models with billions of parameters. So this requires different forms of parallelism, both data parallelism as well as model parallelism to enable this to run at scale. In fact, I'm very happy to hear that recently NVIDIA has been pushing the exascale efforts. So the most recent supercomputer, the Summit supercomputer, had about 3 exa-ops, like exa operations in AI algorithm, in an AI model. So we are really breaking new barriers when it comes to computation. And there, all the way, like in the full stack, all the way from the hardware to different software primitives to algorithms, everything you want to think of it in a more unified manner, right? So how do I design the relevant hardware, the relevant parallelism to run this at scale, and what are the machine learning algorithms that enable that? And many of the classical distributed systems work really is built for a lot of reliability and redundancy, right? You don't want, even if the machines fail, you really want it to be robust. Even if you really want all your data to be really transmitted or received. So can you overcome some of this, right? Maybe are these constraints too rigid? I mean, in machine learning, can we get away with more lightweight systems, but still not lose our final accuracy? Because our goal is really, in the end, to have a well-trained model if we are thinking of the distributed training regime. And so that's where I'll kind of deal with how some of the gradient compression you do during large-scale learning can still preserve accuracy. So there is a notion of free lunch. You don't have to send your complete gradient information. If you just send the sign of the gradients, it turns out that you can preserve a lot of information and even show in theory that this converges well under many reasonable conditions. So again, there is kind of this interplay of how the compute infrastructure and the design of distributed systems for training interplays with the machine learning algorithms itself. Right, so you see like the two pillars coming together. And that's kind of the overall summary that, I won't cover all these aspects in a lot of detail. That's not feasible, but I wanted to give this kind of overarching view on how, there is the trinity of data, algorithms, and infrastructure. And the more holistic way we can think of them together and design all the three pillars together, we can get the best benefits. Again, I'm happy to take questions at any point, so feel free to interrupt me. Great. Yeah, so now let's jump into the data. So as I said, the first aspect is how do we collect data in a more intelligent manner, right? So we don't just passively take all the data from the web or whatever domain we have and just label all of it. Instead, can we be more strategic in our data collection? And so we'll see how active learning can help us with that, and as well as the kind of feedback we get from the annotators. Maybe getting the full information about the label is very expensive. If you could get some partial information, can you still learn from that? And so those are some techniques I'll explore here. And as I said, the next part is on how to aggregate multiple crowd workers or annotators, even when they're making mistakes. How do we design robust aggregation strategies? And the last one is about how we can reduce our sample complexity as well as improve generalization in our machine learning models. And how do you augment your label data sets in different ways? And I'll show two paradigms. One is how we can use generative modeling. So if you can also learn to generate the input, can you use that in your prediction task to improve learning and even do semi-supervised learning, right? The other is domain information. So if you have knowledge of some symbolic rules in a domain, how do you augment that to your numerical training data, right? So usually symbols and numbers usually don't go well together, but what are some ways to kind of put that all together? So we'll see how to do that. So the notion of active learning is quite old and very intuitive, right? So you want to label data based on how your current machine learning model is doing. So the usual setting is a pool-based setting where you have a pool of data that is sent to the labeler, like a human labeler who labels it, and then it's fed to the machine learning model, and in a classical setting, you just retrain your model from scratch again. And you look at how this model is now currently performing, and you decide what new examples should be labeled. Right? So the intuition is you want to label those examples where you're currently most uncertain about. That's because that's where you're having the performance loss, so you want to improve that. And the question is, does this work well in practice? We want to explore that, and what are some variants of this that are, that can even work under, say, robust settings. And the other question is scalability, right? How do I make this work with deep learning? So in the pool-based setting, in the classical analysis, what people do is they completely retrain the model each time new data comes in. And that's just not scalable for a deep learning model. So instead, what we decided was to kind of keep training in mini batches. So you have this incremental training. So you have your current model, you decide what to label, you get these label samples, and you can now mix the old and the new samples in a randomized manner and create new mini batches and kind of keep training. So this is a lot more scalable than each time waiting for it to converge and ongoing. And so the task we chose in one paper, in the Eichler paper this year, was this named entity recognition, which is a sequence tagging task, right? So each token or word in the sequence, you want to say whether it's an entity and what kind it is. And there are some good deep learning models for this, but we also made some improvements there. For details, you can look at the paper. I won't go into the neural network architectures there, but we wanted to ask the machine on the active learning side, how does it perform compared to the state of the art, right? I'll use SOTA for state of the art throughout the talk. And so, as I said, the most natural active learning heuristic is this least confidence heuristic. So right now, this is done at the sentence level, so you can ask what is the sentence that has the lowest confidence. You pick that for labeling. And in this setting, we simulated the labelers because we had the full data set. And so we took the onto nodes, that's the largest benchmark available for this NER task. And we wanted to ask how well can active learning do? So because these are variable length sequences, we also looked at a normalized version of confidence, right? You normalize by the length. Because without that, otherwise you would always pick out like long sentences because they have the lowest confidence. So those were two variants we tried out, and we also tried a Bayesian version. So, what does it mean? Like, what does confidence mean in a deep learning model, right? The typical way we think is the softmax, but that's always may not be the right, notion of confidence. We also looked at a Bayesian version, a Bayesian disagreement score, and in this setting, both of them performed very similar. But I'll just mention how in some extensions there was a difference. So what we see here is the real surprising thing is you can get away with much less data with active learning, as little as 25% of the original data set to get to the state-of-the-art test score on this data set. And the other kind of question is how well would deep learning do with active learning compared to a shallow model, right? Kind of our usual thinking is shallow models will require less data, so if I'm in a regime that's data limited, let me use a shallow model. But it turns out that if you have the flexibility to query data in an active way, you can actually do deep learning even with very little amount of data. So even when the shallow model was given the full data set, the deep learning model with an active learning heuristic required only like 12% of the original data. So, yes, deep models are data hungry, but active learning can be a way around this. And we need a lot of research in this field to kind of, push deep learning into a lot of new domains where there is a lot of, either it's difficult or even impossible to get lots of labeled data, right? And if you see like the normalized length, by the way, has, in the beginning was slightly better than the unnormalized one, which also kind of is intuitive that if you're extremely data limited, you want to normalize for the length because you can be much more strategic in what you label in the variable length setting. And so that's the takeaway that, in this setting, we saw like uncertainty sampling helps. I mean, there are more sophisticated theoretical works on active learning, but usually in practice, we see a lot of simple things work. And kind of the principle is you really push your baselines to the limit and then try the sophisticated algorithms, right? Whereas a lot of academic research starts with an idea that you're really married to, and then you want to really make it work in practice. And so that's where there is a gap between how we have to do empirical research and how it's currently done. And I could go on and on about reproducibility and all the issues there. But this is kind of a setting where that's where we said, let's start with the simple techniques and see where they actually are limiting. And so my collaborator, Zach Lipton, has a series of works on active learning where he further showed that the Bayesian technique was a lot more robust compared to just the softmax. So in this example, we didn't see the difference. So you really want to do an extensive set of experiments to tease out, again, the differences between the algorithms, right? So that's another thing. So just one more thing I want to emphasize is, here, it's an impressive result that we could get to the state of the art with just 25% of the data set, right? So, but what is the corollary of this result? The corollary is maybe this data set is not that diverse and interesting. So right now, we think of the difficulty of a data set by how big it is, right? So we are judging data sets by their size, and we honestly don't have many other measures to think about how diverse or difficult is this data set. So you could think of running active learning heuristics also as a way to judge that, right? Even if you've labeled all your data, you already have a data set, you could think of running these kind of mechanisms to ask, okay, what is, like, if I could do active learning, do I really need all of this data set? And in this case, it turns out you don't. And so that could be a way to compare different data sets and judging the difficulties of training on them. So the next aspect is, so far we said, let's pick which examples to label in an active way. The other thing is, can I also ask questions to the annotators in an active manner? Right? So typically, if you have a large number of categories, you cannot just give a drop-down menu and say, tell the annotator pick one, right? If like ImageNet has 1,000 categories, so you just can't, put an interface of all the 1,000 and ask them to pick out. And in the ImageNet case, how they did it was through a hierarchy. So they used the WordNet hierarchy, and then they asked the annotators binary questions, right? So is this an animal or not? If it's so, then is this a domesticated animal, and so on. So you have this hierarchy, and you're asking binary questions. So, but if you were kind of having a conversation with a human, you would naturally change what you ask based on the information you get, right? So based on the feedback, you want to change that. And so now you have the opportunity also to actively get the feedback. You want to decide where in the hierarchy you want to pick the binary question. Right, so, and the intuition is you want to pick it at a place where there is a maximum uncertainty reduction, right? Because if you're already pretty confident this is an animal, you don't want to ask that question. You want to skip that and directly go to the finance level category as much as possible. Yeah?
What's the impact of errors in labeling? So humans probably make errors.
Yes. I'll come to the next stage. So that's the aggregation stage with the crowd workers. So right now, I'm assuming there are no errors. So try to decouple the two parts. But good question. So right now, we are going to ask these questions, and we're going to pick them in an informative way. Right? So you could think of doing this in an active way on each example. Right? So in each example, you get an answer, and you could maybe jump quickly into the finance level. But then it turns out you can do even better than that. And that's what I mean by partial label or partial feedback, that you ask one question on one example, and depending on the feedback, maybe there's another example that can reduce your uncertainty in the model to the better extent. Right? So you don't want to keep on looking at that single sample until you get the finest category. And so that's what we mean by partial label, that even with partial information, you keep training and you keep kind of going forward with asking more feedback. And so how much does this help? So the yellow line is the one where both the data and the questions are active. So each time you actively pick out which sample you want to label, and also where you want to ask the question, what's the binary question you want to ask, and then move on to another one. So it turns out that if you do this, you can save, you get even a higher accuracy. So the baseline is completely inactive, right? So this blue line is where you're just randomly picking data, randomly picking the binary questions. So compared to that, you see that there is a big saving. You get higher accuracy. You can do it with just 30% of the number of questions you needed to do in the passive case. And you can also, if you want to annotate your data set, your training data to the finest level category, you can also do that with far less labels. Right? So this one is about training and generalizing. This one is just labeling the training data set itself. And both, you get a lot of efficiency by doing it in an active way.
So essentially, are you asking kind of more questions to samples that give you more information?
Yes, indeed. So so it was like entropy and some similar measures we use for uncertainty reduction, and we ask, okay, where is it going to be the maximum reduction? But we also choose the sample and the question, right? So each time we are iterating on that.
So to speak, also the quality of
Yes, indeed. And because if if you have like good confidence on the course level categories, you can just skip them and directly go to the questions that are relevant. Yeah.
So I'm curious how this might correspond with some of the active learning theory in terms of sometimes you're linear in the data set size and sometimes you're sublinear.
Yeah.
And I'm just wondering if there are any theoretical results connecting.
Yeah, that's an interesting question. I'm not sure people have done this in the hierarchical setting, so I think it's open. I don't think it's completely, yeah. Yeah, no, even just the classical setup, I don't think it's been done. So that's a good one, yeah. Yeah, so that's really the takeaway, right? So you want to strategically pick which examples you want to label, and also what kind of feedback you're asking the annotator. And typically, if there's a hierarchy or some structure in your categories or labels, then you can be exploiting that to really reduce the the time and effort it takes from the annotators to label. And and that's the idea. And then you can kind of be training a model much quicker than before. So the next point is about aggregation, right? So, we have labelers that are error prone. It's very expensive to hire experts in most settings, right? So unless it's medical imaging or something where you really need expertise, in most of the other settings, we just like go to Mechanical Turk or some similar platform for labeling. And so when now there is errors, how do you resolve that? So the standard framework is to just do the majority rule. So that's why you have many annotators, sometimes as many as 10 or 20, and then you just say, what is the majority saying? That's going to be my label. But then this is wasteful. I mean, you first of all need many annotators per sample, and the second is, we are thinking there is wisdom in the crowd. That may not always be the case, especially the political scenario we see today. Sorry for it's also me. But anyway, that's right. So so what if there is one expert who really knows the dog breeds much better than the others, right? So in this setting, that's completely just gone. I mean, the machine learning model doesn't even see the variation across different crowd workers, right? Because that's completely hidden. You just filter it before it comes to the machine learning model. But then what if you took directly the raw annotations? There is a lot of information here, right? So if you assume that the annotators are consistently making the errors, like there's just not an awareness of the different dog breeds on one annotator versus the other, then you can learn these statistics as you're training your machine learning model. Right? But the challenge is we usually don't have the ground truth. So in practice, people usually have a small gold standard data set, and they usually use that to screen the annotator. Is this annotator even seriously labeling? I mean, if they're just kind of randomly clicking, right? These are crowd workers on Mechanical Turk where, you're not directly kind of being able to talk to them. You don't know who they are. So usually there's some screening process, but after that, there is no ground truth, right? Because if you had, then you wouldn't be going for this labeling. So when there isn't the ground truth, how do we do this? And so this is a latent variable estimation problem, right? So I want to figure out both the ground truth label as well as the quality of my annotators. And so you can think of different EM-like techniques to do this well. But, so people indeed initially, there have been earlier works that attempted to do this, but the main drawback was they were still going by the majority rule. So they would think about starting an estimate of the annotator quality based on the disagreement with the majority. So I think this is the annotator quality because of how much they disagree with the majority rule. And then you have the machine learning model in the loop and kind of iterate back and forth. So the main change we made instead was to use the machine learning model itself as a surrogate for the ground truth, right? Because think of it, what is the ideal scenario you want? Ultimately, at the end of training, you want your machine learning model to be very accurate, right? So it should be outputting all the ground truth. And at the same time, you want all your annotator quality to be accurate. So if you start at a good initial point, you can now imagine both help each other. Like the annotator quality models get better, your machine learning model also gets more accurate, so they can help each other. So, and in that intuition, this is the way we designed the algorithm, where initially we said, okay, everybody is accurate, right? Everybody is 100% accurate, train a machine learning model. And so now, based on like what the model is saying, what the ground truth labels are, based on that posterior, right? So you can like now, you update the posterior of each annotator based on the machine learning model. And then based on that, you retrain your machine learning model with a weighted loss minimization. Because now you have an estimate of what the different qualities are, you retrain it, and you repeat that again, right? So you can repeat this process again and again. And so what is the benefit of doing this? So in a way, because you're not directly querying to the majority, but to the machine learning model, it hopefully kind of is able to also overcome the stupidity of the crowd, if that's the scenario that arises. As long as the errors are fairly random. I mean, this, in the adversarial case, this would still fail, because if everybody else is banding up against this one worker and then kind of always consistently giving an answer in another category, this would be hard. But if their errors are fairly random, right? Because if this one expert is consistently picking this category across different examples, while everybody else is randomly making mistakes, the machine learning model is able to overcome that.
So I was going to ask about the adversarial side. Have people looked at what percentage of Byzantine adversaries this type of approach would?
Not that I'm aware of. There hasn't been a theory that I'm aware of, which would be very interesting. Yeah.
What if it's not entirely random, if there's a correlation between some of the annotators?
Yeah, so that's kind of, the adversarial would be the extreme version of that, right? So there hasn't been an analysis so far. Which is, in the mechanical Turk setting, it could happen, but you usually think, workers have registered and, don't have any kind of, but yes, it's interesting. It can happen, but people haven't studied that much so far. So what's the theory we analyzed here? So the question was, we have a fixed annotation budget, right? So it's in terms of like how many labels or, in total we can get, or how many annotations. And so there are different strategies. You can just have a small training data set and employ a lot of annotators for each example. Or you can say, you can spread out. You have few annotators, but more examples. So in the end, what you care about is generalization. You really don't care about your training data to be extremely accurate, right? That's typically not the goal for machine learning. In the end, you want the model. And whereas most of the earlier crowdsourcing strategies has been to really make the training data highly accurate. Whereas in fact, in machine learning, we are adding noise, right? We are adding all kinds of noise to regularize and help training better. So it turns out that you can prove a generalization bound that shows that having just single annotation per example is the optimal thing, which is intuitive. If you have a fixed budget, you're better off getting more labeled examples, right? That should improve your generalization. And the fact that even though there is label noise, we can kind of, we are learning that in the loop, and we are learning the right weights for different annotators. We can, therefore overcome the effect of label noise as long as it's not overwhelming, as long as it's limited. So I showed a special case here. We have the general case where workers have different qualities. But in the special case, you can think of intuitive assumptions, right, when this would work. One is, first of all, the worker should be fairly correct. If they're different workers, then you can also, have more general assumptions. Because everybody is the same, if they're all wrong, obviously you're never going to get to the correct answer. And the other one is you want the machine learning model to be accurate enough, right? Because this is a generalization bound, you're looking for the best predictor, you assume that that's accurate enough. Because you're going to use that as a surrogate for the ground truth, and if it never gets good, there is no hope of ever getting to a good answer. And so these are natural assumptions for the theory. And also in practice, we do find that there is a gain by just limiting to a single worker and instead having more examples for training. The main challenge here was actually finding open source data sets with identities of annotators, right? Meaning, which of the annotators labeled which example and in what way. Because most of that is filtered out, and you have the cleaned up data sets that are available for the public, and that's a huge challenge to do crowdsourcing research. So if somebody is thinking of collecting data, please keep all this information well documented, because that can help us further use that for improving crowdsourcing. Great, so this was about how we can improve both the data collection process and the aggregation process by putting machine learning in the loop with our machine learning, with the data collection process. So in the next part, I want to ask how we can augment our data better, right? To generalize better. In practice, as I said, usually in computer vision, it's very simple things like you crop the image, you add some noise. But if you had better information about how each image is generated, you could potentially come up with better data augmentation, right? So think of if you know all the variations of what a dog looks like, right? You could kind of augment your training data to generate all those examples and train a better predictor. So GANs have been very popular for generative modeling. You see very good-looking images of GANs, including some of the latest ones, right? It's almost amazing. Oh, did a machine generate it, right? But on the other hand, it's actually not very suitable for downstream prediction tasks, because first of all, there's no information about the prediction that's used in training the GAN, right? So the kind of feedback that it's getting is whether this image is fake or not. So for instance, if you're predicting whether this is a dog or a cat, does it really matter if this is fake or real, right? So it's not clear that's the right feedback to use for a predictive task, right? And the other is there are lots of challenges in training GANs. You can't just pipeline a GAN into your prediction task, right? Because there's all kinds of junk images that look nothing like a natural image that are generated. So how do we overcome all those issues? So in a recent work, what we asked was, can we try to have one model to do both prediction and generation? This is very difficult. That's why people have thought about it, but not really made a lot of progress before. But what is new here, right? So the main challenge is, if you're thinking of prediction, you go from your input to your output label y. So output label y is typically of a lower dimension than the input, right? So there is information loss when you go forward. In a feed-forward neural network, it's very clear. In fact, with the convolutional layers, you're reducing your dimension through spatial pooling and other operations. So there is information loss when you proceed from X to Y. And so you just can't reverse it, right? You just can't go from Y to X and just reverse the connection. So that won't work. People have tried to train reversible models, but even at least at the last stage, you still have to lose information, and it's very difficult to train them. So, so what we decided was, is there a way to not try to do a reversible model, keep the predictive model, let's say, to be a convolutional neural network, which we know has state-of-the-art performance, but instead design priors that try to reverse the process, right? So now I have a probabilistic model to generate from Y to X, but that will, the inference in this model is going to be reducing to a convolutional neural network. So it's going to be design of structured priors so that the inference in this model will be the same as a convolutional neural network. So the details are in the paper, but the main intuition is you now have like, what we call rendering. So the rendering is the reverse of filtering, right? So both there is like the fully connected layers and like the convolutional layers as in a CNN. But you also have now hidden variables that, look at how to go from a coarse resolution to a finer resolution. Because the spatial pooling is doing the reverse, it's losing information. So when you try to go from a coarse to the finer resolution, you need like some stochasticity because you're not certain what that process is, right? So that's why we introduce these hidden variables. And that's the main aspect of the paper. So I won't go into the details, but as you can imagine intuitively, like, in the convolutional network, you're feed forward, you're doing pooling, you're doing all these operations in a forward manner. In the generation, you're doing rendering. So you're going from a coarse resolution to the finer one. And with the hidden variables, you're capturing the uncertainty in going from the category to the image. And by the way, it turns out that so far, this does not generate very good-looking images, right? That's not the goal of this work. But the goal is really to ask how we can augment our training data, how we can better regularize, better generalize, using this kind of structured prior information of the generative model. And in fact, it turns out we can come up with even a better loss function than the standard cross-entropy loss function with this one. I won't go into the details, just kind of the intuition is mostly when we think of cross-entropy loss, we are maximizing the posterior for the correct category. Right, so we want to like kind of, really get the correct category right. But we are not thinking of the incorrect categories. So you also maybe want to push down the incorrect categories. And so you can have two different networks to do that. So I won't go into the details, but it's kind of an intuitive thing that you want to both think of the correct and the incorrect categories, not just the correct category. And so that improves generalization, as well as a new form of regularization. So if you now have the generative process, you can think about all the active paths in this, like how you go from the coarse to fine resolution. You can like look at the paths here and regularize those paths. And it turns out that this really helps both in theory and in practice, like the right measure of function class complexity for this class of models. So there's a lot of intuitive understanding that having generative information will improve generalization, but you can also analyze the generalization bounds and ask how exactly does it improve. And so in the paper, we have all the state-of-the-art results on benchmarks for semi-supervised learning that this model achieves. So since I'm really out of time, I want to kind of skip the next one. I don't want to cover this in detail, but just kind of give an intuition of how, in a standard neural network, we just have input and output and one loss function, and we really try to fit for that function, right? And with this, you can only achieve interpolation because you can only kind of figure out what, how to interpolate these examples. You can't extrapolate beyond what you haven't seen. Right? And you also won't know how the different functions are related to one another. On the other hand, if you have like symbolic expressions or equations or inequalities, you can use that to do meta-learning on the entire domain of functions. And so that's what we did in one of the ICLR papers on how to put them together. The main kind of thing to note is like you can use trees and tree LSTMs to encode both symbolic data and the numerical data, right? So the main kind of aspect is, we decided to also encode numbers through a decimal system. Like, you can think of, how is this 2.5? It's really through this set of operations, right? So you can have like a tree representation for numbers as well as for equations. And so this way you can have a common representation for both numbers and symbols and employ both the information together when training for an entire domain of functions and generalize to even like higher depth trees. So you can verify equations, you can complete equations, as well as you can look at evaluating functions. You can do multiple tasks and learn multiple functions within the same framework. And really the kind of unifying viewpoint here is there are trees of different kinds, and that way you can unify them. So, and there are lots of kind of evaluations we have there. So let me see here. How do I kind of skip slides and go forward? Do I have to run through all of them, or is there a way to directly skip a section? Otherwise, I can run through it, but it's going to be a...
I will ask one question
Yeah.
regarding what you mentioned
Yeah.
before. So my understanding is you're trying to at the same time augment the data and train the learning algorithm at the same time, so to speak.
Yeah.
Would you guys compare to the setting where you use GAN to generate the data?
Yes,
Kind of offline, right?
Yes,
And then generate
exactly.
the data, put it to train
Yeah.
the classification
Right.
algorithm with the augmented data.
exactly.
How did it compare with that?
But the other benchmarks were all on GANs. The benchmarks had like GANs, the previous algorithms, and we either beat or match that in many settings. And it's kind of like, like as I said, if the goal is not to generate visually good-looking images, this one seems to do very well on semi-supervised learning benchmarks. Yeah, I can. So, sorry. So as I said, the algorithms, I won't have the time to go in detail. I want to just kind of, away from here, quickly point out that, in terms of software frameworks, indeed, a lot of progress in deep learning has been with the use of very flexible and easy to use frameworks, right? And if you're interested in exploring how tensor computations or tensor operations can be useful in various machine learning tasks, I encourage you to explore TensorLy. It's a Python front end. Think of it like a Keras-like front end, right? So you can connect to different backends. You can have PyTorch, TensorFlow, or even just the usual NumPy. So you can switch the backends and just code in Python. And there are many well-known tensor algorithms, as well as different tensor layers you can put in your deep network. So this really lets you explore a range of different architectures that may be suitable for your application. So there are lots of example Jupyter notebooks, I encourage you to go and check that out. The other one I'm very excited about, that's a recent foray for me, is putting together different areas to have autonomy, right? So indeed, self-driving cars and all the different application for autonomous systems, there's a lot of interest, but also a range of challenges. So at Caltech, our vision is to ask how we can bring these different disciplines together and have a common framework and language for people from different disciplines to interact. So one of the things I'm very excited about, I know the volume is a bit, so this is a drone testing laboratory where there is, that kind of what you see panel here is programmable fans. I guess maybe you'll see the wind a bit later. So there is a lot of ability to program wind conditions, and there's an array of cameras that can precisely record measurements. So you can outfit the drones with all kinds of sensors. And nothing like this exists anywhere else as far as I know. And so we plan to release all these data sets for people to then explore different algorithms, right? Because a big challenge with robotics and especially drones is we don't have actual measurements from different drones, right? We only have, we have various simulations, we have various understanding of fluid dynamics that's incomplete. But with this facility, we really hope that we can get precise measurements and really push for different algorithms. So anyway, that's with the facility. So one example I want to show is our preliminary work on how, so this is the standard PD controller where there is no learning, right? So this is designed based on a known physical model, a fluid dynamics and all kind of interaction model for the drone. And the other one is a neural lander where, we emphasize we're not learning everything from scratch. I don't think you should ever do that in any autonomous system. But instead what we said was, what's the unknown part of the model. So it turns out that the ground effect is a crucial challenge for drones. Like, if you have seen any of the commercial drones, right, when they go to land, they're extremely slow. They're inching little by little because it's really not well understood how the aerodynamics forces interact when it's landing. So that's a very highly complicated fluid dynamics model, and people haven't figured that out. And so instead, can we now, if we have data, so in this case, there were no external wind conditions. That's kind of our future work. In this case, it was just ambient conditions. But we have sensors outfitted, and so we can look at landing conditions with just the standard controller, the PD controller, and then train a machine learning model just for the unknown aerodynamics effect. And then we'll use that to correct our controller, right? So as you can see, it's only limited learning. It's not learning everything. And that's kind of, you want to utilize all the domain knowledge and kind of augment your controller. And the other interesting thing was, it turns out that just a plain neural network didn't work. In fact, some of the drones crashed and, the wings broke. So there was, it turns out that, in control, what you really care about is stability, right? So you want to ask under bounded disturbances in the input, can you have bounded disturbances on the output, right? Or bounded variations in the output. So if you spectrally normalize your neural network, then the Lipschitz constant is limited and you can guarantee this under some conditions. So this is also a guarantee we derived that for these networks, you can guarantee stability. And it turns out in practice, that's the one that worked. So it was, again, nice to see theory and practice coming together and just kind of, if you just took a neural network out of a box, it didn't work, right? So that was kind of nice to see. So as you can see, that one on the left is just without learning. So, this is just taking off. Both are similar. But notice the landing. That already landed. That is like kind of hovering forever. Right, so it's, and we have like all precise measurements in the paper, so there's a lot of improvement you can do on just the landing aspect, and there are so many other settings that we can improve with learning. Great, so at NVIDIA, I'm very excited about a new venture I started 2 weeks ago, and starting a new research group that focuses on core machine learning as well as looks at how that relates to different domains. There is indeed an exciting research environment at NVIDIA, lots of research leaders, including some of the recent hires. In robotics, we have Dieter Fox, computer vision, Sonia Fiedler, Brian Catanzaro in applied research. So there is the traditional areas of architecture, VLSI, as well as machine learning, all coming together. So lots of internship and full-time opportunities. It's an open, publishable environment, as well as lots of very relevant applications that we are focusing on. Yeah, so to conclude, I try to cover a broad ground of how we want to think of AI as having 3 pillars: data, algorithms, and compute infrastructure, and how new research has to focus on bringing all these 3 together, right? How to incorporate the data constraints and labeling frameworks, the system constraints, software frameworks, all these together when we design algorithms and models. And this work has been thanks to so many amazing collaborators. I won't be able to name them individually. They are interns, my own PhD students, different faculty collaborators, as well as scientists and engineers at both Amazon and now NVIDIA. So thank you.
So we're over the time, but I guess we have time for like one quick question or so. Do we have a microphone as well? Any questions from the audience?
Hi, thank you for the talk. So one part of your talk that got missed out on was the scalability part,
Yeah.
and I don't think this works. Okay, so a lot of the work for scaling up tensor factorizations focuses primarily on sparse tensors, so the real world.
Not necessarily. So the ones we've studied has been, dense, right? But looks at like randomized projections, like how, you have like a whitening step that looks at singular value decomposition to first reduce dimension. And there you can use randomized techniques. And so all these are very scalable and they don't require sparsity. Yeah.
Thank you. So it's more an overarching question. So I teach computer vision. So now there's this hype. I mean, I can say it, hype for good. Deep learning solves everything automatically.
Yeah.
And when I teach this class, students may ask me, why do I have to learn all these fundamentals, like optical flow, camera calibration? It's all done automatically. So what is your take on us to teach the future generations?
Yeah, I mean, I'm also debating this all the time, right? And so I'm kind of, this is where I would like to kind of think of, I'm going to teach in winter, and I'm planning to see how we can get algorithms to fail or, naive things to fail, like let students really see, when it's failing, what do you do? How do you debug, right? That's when you need all the understanding. That's what, differentiates an expert from a novice. So, how do we design like a course curriculum that teaches them how to debug within a structured environment? I mean, if no one knows what the answer is, then they're kind of, like we don't know, right? So how do we come up with examples where that demonstrates that just a naive technique didn't work? I mean, the drone was one example. It actually crashed. So, like the students could see, oh, this really doesn't work. So maybe examples like that where, showing like if you just like, okay, you train your model, do the baseline, and oh, this is actually, has all these shortcomings. I don't know, yeah.
Well, Anima is going to stay with us for almost the entire day, so I suggest we take the remaining of the questions offline then.
Yeah.
Thank you so much.
Thanks so much.